1948. The shooting war is over, but the war on geography has just begun. While the rest of the world rebuilds, a rogue dealer named Buster Peterson locks the doors of his California workshop to commit an act of industrial mutiny. The air is thick with smoke as he saws a factory-fresh chassis cleanly in half. He bolts two engines into a single frame, creating a leviathan that forces one operator to fight two throttles and two gear levels simultaneously just to keep it on the road. This Frankenstein experiment forced a billion-dollar company to surrender and gave birth to the Caterpillar D9. But looking at the scars it left on the planet, you have to ask, was this the tool that finally civilized the world, or the weapon that destroyed the wild forever? With the global conflict resolved, the industrial world pivoted to a new enemy, the landscape itself. Global reconstruction was underway, and back in the United States, the federal government authorized massive hydroelectric projects, like the Garrison and Hungry Horse dams. The scale of these earth-moving demands was unprecedented, and it quickly exposed a critical deficit in the industry's arsenal. Contractors assessed their fleets and realized their primary weapon, the Caterpillar D8-2U, was simply too small for the job. The D8 was the standard bearer of the era, but post-war projects required moving entire landscapes, not just grading roads. A gap opened in the market for a high-output dozer capable of handling millions of cubic yards of rock. Caterpillar, entrenched in a conservative engineering culture at the time, was slow to fill this void. This delay forced the men on the ground to improvise. Dealers and struggling contractors stopped waiting for the factory in Peoria and decided to build the solution themselves. The most significant of these experiments came from a dealer named R.A. Buster Peterson. Peterson looked at the D8s in his inventory and concluded that the only way to double the power was to physically double the tractor. Peterson's team began modifying stock units, sawing two D8 chassis in half to create what the industry would call the Siamese D8. They removed the interior crawler and final drive assemblies from two separate machines. To maintain structural integrity, they fabricated a massive hard bar and used custom steel plates to bolt the chassis together into a rigid, singular frame. The result was a mechanical leviathan producing nearly 300 horsepower. Building it was one challenge. Operating it was another. Peterson pioneered a system consolidating the controls into a single station. One operator had to manage two throttles, two gear shift levers, two steering clutch levers, and a master clutch simultaneously. Between 1949 and 1952, Peterson purpose-built 3 of these units and sold kits for several others, clearly demonstrating the demand Caterpillar had ignored. The Twin D8 found its true calling in the brutal terrain of the Hungry Horse Reservoir project in Montana. Here, the machine became the anchor for the highball clearing method devised by contractor J.H. Trisdale. This operation involved 2 massive tractors driving parallel along the ridges, hundreds of feet apart, dragging a loop of heavy steel cable between them. The key innovation was a 4.5-ton steel ball, constructed of 3/4-inch boilerplate attached to the center of the cable. As the Twin D8s tracked forward, the ball lifted the cable, creating the leverage necessary to snap ancient timber or uproot it entirely. This method allowed crews to clear snags and timber at an industrial pace, keeping the project on schedule despite the punishing landscape. The success of the Twin D8 proved that a dual-engine output could move Earth exponentially faster than a single unit. This forced the executives in Peoria to confront reality. The future belonged to high-horsepower applications, and Caterpillar was losing the race to its own dealers. Caterpillar responded with the D9X program. Engineers knew welding 2 engines together wasn't a sustainable manufacturing strategy. They needed a purpose-built machine. Prototypes were built in 1954, but scaling up the engine size presented a major engineering hurdle. The standard mechanical transmission could not handle the shock loads required to push that much weight. If a machine of this size hit an immovable rock with a direct drive system, the torque spike would strip gears or stall the engine. The solution was the torque converter. This fluid coupling replaced the direct mechanical link between the engine and transmission, allowing the engine to maintain RPM even when the tracks were stalled against a load. Instead of stalling, pressure built inside the converter, multiplying torque and delivering a smooth, constant wall of force to the tracks. When the factory-built Caterpillar D9 launched in 1955, boasting 286 horsepower, the company offered a strategic choice: Customers could select the 18A series with a direct drive transmission for drawbar efficiency, or the 19A series equipped with a torque converter for heavy dozing. The king of crawlers had finally arrived. It was no longer a garage experiment, but a refined industrial tool capable of work that was previously impossible. But a king needs a kingdom. As the D9 rolled off the line, President Eisenhower was looking at a map of the United States, realizing it was time to redraw the lines. Redrawing the map required a tool that didn't just scale up existing technology, but revolutionized it. This demand ushered in the golden age of earthmoving, defined by a machine purpose-built to alter the planet's surface. The D9's dominance relied on a specific innovation integrated deep within its frame: the turbocharger. The power plant was the new D353 engine, a massive 6-cylinder diesel with a 6.25-inch bore and an 8-inch stroke. By using a turbocharger to force air into the combustion chamber, Caterpillar increased the power density significantly without making the block geometrically impossible to mount. However, generating power is distinct from delivering it to the ground. This distinction sparked a debate between operators and engineering. Operators accustomed to the feel of the load preferred the mechanical connection of a direct drive transmission. Engineering, however, knew that the torque spikes produced by the D353 would cause catastrophic drivetrain failure if an operator dead-stopped against a rock. The engineering solution eventually evolved into the torque divider system. While early D9s offered a binary choice between direct drive or a torque converter, later models standardized a hybrid design. This system routed 70% of the torque through the converter and 30% through a direct shaft. It was a brilliant compromise, offering the drawbar efficiency of a direct drive while retaining the shock load protection of a fluid coupling. High output creates intense heat. To prove the cooling systems could survive, Caterpillar punished the prototypes at the Arizona Proving Grounds in the Tanaja Hills. In the baking desert sun, they pushed the thermal limits of the engine and hydraulics, ensuring that the D9 working in the American Southwest or the Middle East wouldn't fail mid-shift. When the D9 hit job sites in 1955, supported by industrial films like The Big Track, it promised to do the work of two. The math supported the claim. A 1957 report demonstrated that a D9 push-loading a Cat DW21 scraper could load 25 cubic yards of earth in just 45 seconds. This effectively halved loading times compared to the D8 and eliminated the need for tandem push tractors. In an era of rising labor costs and shrinking timelines, the D9 became an economic necessity. This capability fundamentally changed how contractors approached excavation. The D9 had enough tractive force to drag a giant steel claw, known as the Kelly Ripper, through the earth. Previously, hitting bedrock meant bringing in drill crews and dynamite, a slow, expensive process known as drill and shoot. The D9 could now rip bedrock through sheer force, reducing excavation costs by 30 to 50% and accelerating the construction of the interstate highway system. However, this golden age had a dark side. Early D9s were open cab units, offering no protection for the operator. As machine capabilities increased, they were deployed on steeper slopes to utilize the rippers. If a machine rolled, the operator had little chance of survival. The D9 earned a grim reputation in extreme terrain, and it wasn't until 1972, following the introduction of specific OSHA standards, that ROPS, rollover protective structures, became mandatory, enclosing the operator in a steel cage capable of withstanding the tractor's crushing weight. By the time the D9 crossed the Atlantic to assist on the M1 motorway in Britain, it was an icon. The British public viewed these yellow giants with awe, turning earth-moving into a spectator sport. Caterpillar enjoyed the global dominance, confident that no manufacturer could challenge the king of crawlers. But history punishes complacency. While Peoria celebrated its victory, a company in Japan called Komatsu was quietly analyzing the D9. They weren't just admiring the engineering, they were designing a machine specifically intended to dethrone it. That dominance was showcased on the vast King Ranch in Texas, where the D9 proved its utility extended far beyond moving rock. Here, units were fitted with specialized implements like the Holt funnel dozer and the root plow to combat invasive mesquite. These massive attachments required the D9's tractive effort to shear roots deep underground, demonstrating that high horsepower was essential for heavy agricultural clearing, not just excavation. However, while Caterpillar solidified its hold on the American landscape, the storm across the Pacific had made landfall. By 1969, the threat was no longer theoretical. Komatsu launched the D355A, a machine engineered to exploit the limitations of the existing Caterpillar D9H. The D355A was not a cheap imitation, it was a superior heavyweight contender. Powered by the SA6D155 engine, it delivered 410 horsepower, going toe-to-toe with the Cat. Crucially, the Komatsu was heavier, providing better penetration in hard rock. Compounding the problem for Peoria, a weak Japanese yen allowed Komatsu to price this machine 30 to 40% lower than the D9. The siege of Peoria had begun, and Caterpillar's market share began to bleed. Management realized that incremental updates to the D9H, the last of the conventional tractors, would not repel this attack. The D9H was a legend in its own right. It was the pinnacle of the traditional track-type tractor, loved by mechanics for its straightforward design and by operators for its reliability. Retiring the H was a gamble that risked alienating the company's most loyal customers. But to beat Komatsu, they needed a radical platform change. Under the guidance of engineers like Ron Krolak, the design team produced a concept that defied convention: the D9L High Drive. First seen on the massive D10, this design lifted the drive sprocket above the track frame, giving the tracks a triangular profile. This was a functional necessity, not an aesthetic choice. By elevating the sprocket, Krolak's team separated the final drives from the track roller frame. This isolated the sensitive planetary gears from ground-induced shock loads. When the track assembly slammed into a boulder, the impact was absorbed by the main frame, leaving the drive system suspended safely above the impact zone. The transition from the H series to the L series also introduced modularity. On a D9H, a major powertrain failure could sideline a machine for days of heavy wrenching. The D9L was designed with modular components that could be swapped out in the field in hours, drastically reducing downtime. The High Drive also revolutionized how the machine engaged with the terrain. The design utilized a fully suspended undercarriage with a bogie system, allowing the track rollers to ripple over obstacles rather than climbing them rigidly. The ride was so smooth that early test pilots initially rejected it. They complained the suspension dampened the vibration so effectively they couldn't feel the load. However, the data overruled them. Because the tracks maintained consistent ground contact, the High Drive system delivered 15% more tractive effort than the rigid undercarriages of the D9H. To deliver the counterpunch to the Komatsu D355A, Caterpillar paired this new chassis with differential steering. Traditional bulldozers, including the Komatsu and the older D9H, steered using a clutch and brake system, stopping one track while the other continued to rotate. This dead track turn meant the operator lost 50% of their momentum and pushing force during every correction. Caterpillar's differential steering used a planetary gear set to accelerate one track while slowing the other. For the first time, a dozer could turn while pushing a full blade load, maintaining live power to both tracks throughout the maneuver. This gave the new 460 horsepower D9L a decisive tactical advantage, allowing it to outwork the heavier Komatsu in the cycle. The elevated sprocket had proven its worth, securing the D9's position against the mechanical challenger. But, having defeated the threat from Japan, the D9 was about to face an opponent that couldn't be engineered away: the frozen ends of the Earth. At 50 degrees below zero, standard metallurgy fails. Ordinary steel, which performs reliably in temperate climates, hits its ductile to brittle transition point in the deep Arctic freeze. It loses all elasticity. If you strike a standard bulldozer blade against granite at these temperatures, it doesn't dent or deform, it shatters like glass. Ripper shanks snap, track pads crack, and structural castings develop stress fractures. Rubber hoses fail, and diesel fuel clouds and gels clogging the fuel system. This was the hostile reality waiting for the Caterpillar D9 as it marched north to tackle the massive civil engineering projects of the 1970s. The Trans-Alaska Pipeline System, TAPS, was less a construction project and more a logistics war against geography. Engineers had to lay 800 miles of steel pipe across mountain ranges and frozen tundra to move oil from Prudhoe Bay to Valdez. The primary obstacle was permafrost, ground frozen for consecutive years, acting essentially as concrete reinforced with ice lenses. The D9 was the only machine with the sheer mass and hydraulic force to rip through this frozen armor. However, the environment fought back with a phenomenon engineers call cold soak. When a 60-ton machine sits idle in the Arctic winter, the cold permeates every component. Engine oil thickens into a tar-like sludge, and hydraulic fluid turns to jelly. If an operator shut down a D9 on the North Slope, there was a real possibility it would not start again until spring. The solution was as crude as it was effective. They simply never turned them off. For months through the 24-hour darkness of the polar winter, the massive diesels idled continuously. This created a permanent ice fog hanging over the camps, accompanied by the low-frequency drone of thousands of engines. To keep these machines alive, mechanics relied on ether injection systems for cold starts and industrial Herman Nelson heaters to pre-warm any unit that absolutely had to shut down. It was in these freezing conditions that the high drive system, introduced later in the pipeline era, proved its worth beyond just protecting the final drives. In older oval track machines, snow and slush would pack tightly into the sprocket teeth and the roller frames. As the machine sat idle or the temperature dropped, this packed snow would freeze into a solid block of ice, seizing the tracks or stretching them until they snapped. The high drive's elevated sprocket system naturally shed this material. Because the drive gear was lifted out of the muck, gravity helped clear the snow before it could pack and freeze, reducing undercarriage wear and keeping the D9 mobile when other machines were frozen to the ground. While Americans wrestled with the pipeline, a different battle was reshaping Quebec. The James Bay Project was a hydraulic initiative of staggering scale. The critical moment came in November 1978 with the closure of the La Grande River. D9s worked feverishly from opposite banks, dumping massive boulders into the freezing water to form a cofferdam. It was a race against the current, with the reservoir rising 141 feet in the first week alone. But here, the enemy wasn't just the cold, it was the ground itself. In warmer months, the subarctic terrain thaws into muskeg, a saturated peat bog capable of swallowing heavy machinery whole. A standard D9 concentrates 50 tons onto relatively narrow track shoes, creating high ground pressure that sinks deep into soft peat. To solve this, Caterpillar deployed specialized wide track configurations. By fitting the D9 with extra-wide track shoes, engineers distributed the machine's 50-ton mass over a much larger surface area. It was the mechanical equivalent of a snowshoe. While a standard D9 concentrates its weight to crush rock, these modified units reduced ground pressure significantly, lowering the PSI enough to prevent the machine from shearing through the delicate top crust of the peat. This allowed the Iron Giant to navigate the sponge-like muskeg of the Canadian Shield without sinking to its frame, transforming the D9 from a brute force instrument into a tool capable of traversing ground that would swallow a standard tractor whole. This adaptability cemented the machine's reputation at the bottom of the world. In Antarctica, the United States relied on these tractors to carve runways out of blue ice and maintain station infrastructure. To ensure visibility in whiteout conditions, the Navy requested these machines be painted International Orange rather than the traditional Caterpillar Yellow. The distance from civilization meant reliability was a survival requirement. If a final drive failed on the polar plateau, there was no dealer service truck coming to fix it. The D9 became a lifeline for research stations, towing sled trains of supplies across crevasses. The danger was so real that operators often removed the cab doors, ensuring a quick escape if the machine broke through the sea ice. The cabin designs also had to evolve. The open-air convertibles of the 1950s were replaced by fully enclosed pressurized cabs. In the extreme frontier, these weren't just for rollover protection, they were life support capsules. Equipped with heavy-duty heaters and double-paned glass to prevent frosting, they isolated the operator from wind chills that could freeze exposed skin in seconds. By the end of the 1970s, the D9 had proven it could work anywhere. It had ripped rock in the desert, paved the interstates of America, and pushed snow at the poles. It arguably held the title of the most versatile earth mover in history, large enough to move mountains, yet small enough to be transported to the most remote corners of the globe. But in heavy industry, perfect is a moving target. As the 1980s approached, the global mining sector shifted strategy. Pit mines were getting deeper, haul trucks were getting larger, and production quotas were increasing. The D9 had conquered every continent, but it was about to look in the mirror and realize that in the new era of mega mining, being the king of crawlers might no longer be enough. For decades, the D9 was the undisputed heavyweight champion of the job site. If you saw one on the ground, you knew it was the primary prime mover. But in the 1980s and 90s, the global mining industry adopted a new philosophy: sheer, unadulterated scale. This era sparked the size wars. Caterpillar superseded its own flagship by introducing the massive D10 and the Colossus D11. These machines were engineered to match the growing capacity of mining haul trucks, which were rapidly scaling up to the 200 and 300-ton class. Suddenly, the D9 was no longer the headline act. It was shifted to a support role, cleaning up the spillover at the shovel face or ripping material for larger D11s to push. Then, the rivalry escalated. Komatsu deployed a nuclear option on the market, the D575A Super Dozer. Weighing in at over 330,000 pounds and producing 1,150 horsepower, it wielded a blade with a capacity exceeding 120 cubic yards. It was designed specifically to dwarf the Caterpillar lineup and claim the title of the largest bulldozer in history. On paper, the D9 looked underpowered and obsolete compared to these new Leviathans. But the reality of the construction site has a way of checking engineering ego. The Super Dozer was a logistical nightmare. It was so massive it had to be disassembled into 6 to 8 separate heavy haul loads just to move to the next hill. It was immobile between job sites, too big to survive in a market that demanded flexibility. The D9, however, occupied the Goldilocks zone. It was heavy enough to rip through hard rock, but agile enough to be transported on a standard heavy haul trailer with minimal disassembly, usually requiring only the removal of the blade and trunnions. While the giants were captive to open pit mines, the D9 was building highways, clearing forests, and grading developments. It survived the size wars by proving that utility outperforms vanity. But the challenges didn't stop at physical size. The next threat came from the EPA. Modern Tier 4 final mandates threatened to choke the diesel engine. The requirements for cleaner exhaust were so strict that many feared the iconic torque of the D9 would be strangled by particulate filters and sensors. Caterpillar responded with ACERT, Advanced Combustion Emissions Reduction Technology. Instead of simply restricting airflow to trap soot, they redesigned the combustion process. By utilizing series turbocharging and variable valve actuation, they managed to burn fuel cleaner without sacrificing the breakout force required to push a mountain. It preserved the machine's performance while satisfying the regulators. This evolution brings us to today. The machine that started with reckless welding and open-air cabs is now entering the digital age. The most dangerous jobs, reclaiming old mines and pushing loose soil over steep high walls, no longer require a human in the seat. We now see D9s equipped with CAT Command remote control systems. The operator sits in an air-conditioned trailer miles away, guiding the 50-ton machine with a joystick and a screen. These systems allow operations in high-risk zones, effectively removing the operator from the line of fire while maintaining productivity. The machine takes the risk, so the human doesn't have to. This longevity is rare in the industrial world. Most machines from 1955 are museum pieces or scrap metal. The D9 is different. It remains in the catalog, on the job site, and stands as the benchmark for earth-moving. From the crude welds of the Siamese units to the digital precision of remote-controlled reclamation, it has shifted from conquering nature to helping heal it. Modern D9s use semi-autonomous grading technology with 3D digital maps to restore natural drainage patterns, essentially using the blade to print the landscape back to its original form. That spark ignited a journey that took the Caterpillar D9 from a desperate garage fix to the mechanical fulcrum of the 20th century. It rose from the crude welds of the early Siamese D8s to survive the trap of giantism and the invisible enemy of regulation. Along the way, it transformed from a blunt instrument of destruction into a precision tool for reclamation. Today, digital operators control this massive force remotely to heal the landscapes it once reshaped. Ultimately, this machine proved that humanity never really needed to go around the mountain. We could simply go straight through it.